All right, part two of the Intro to Quantum Computer Music. Let's go. So welcome back again. My name is Omar Costamido. As co-pilot, I only have Paulo Itaburai that you've met yesterday. And first of all, I promised that I would answer your questions. So I saved your questions. And here I am answering your questions. So an anonymous attendee asked, it appears Max is not free, has a 30-day trial. Is this correct? Well, yes, it has a 30-day trial, and yes, it is a commercial product, but you can actually use Max for free for an undeterminate amount of time. The only difference, as far as I know, is that you cannot save your patches, but you can open anyone else's patches and do changes. But if you want the ability to save your own patches in your changes to the patches that you open, you either need to be on the 30-day trial or have a license. And there are many options, educational licenses. I noticed that other people started answering some questions from other attendees, which was great. And I was so happy that everyone was really engaging and interacting. And so I also selected another question. Oh, sorry, this one. Actually, these were two people, and I'm not sure if we're two different people, but probably someone asked to the previous question. That's why I asked about PD earlier, and then someone else said, also, there is a plugin for Python, so you could probably just use Qiskit directly, albeit not as nicely as demonstrated by Omar in Max. And the real reason why I selected this excerpt was just for this part, really. Like, thanks. No, in all honesty, there's two parts to this. First one, PD. So PD is a very similar programming environment to Max. It's also a visual programming environment made for musicians and artists. And it is free. There's no commercial side to it. But it is also kind of a simplified or a simplified version of Max, or it only has the core elements of Max. It is written by Miller Paquette, who is a genius of his own time. And Miller Paquette also actually happens to be one of the original creators of Max. So he originally created Max, and then he left and created PD. And so there's a whole community of PD enthusiasts that build extensions for PD, but there's less of a control over how up to date those packages are running with latest versions of PD. And really, I think as far as I know, the only person to really continue to develop PD is the original creator, Miller Paquette, who's a wonderful person. And if you ever have an opportunity to sit on a lecture or a recital where he's at, please definitely do that. And then someone said, also, there is a plugin for Python. This idea of Python and Max or Python and PD and connecting basically a computer science environment and a computer music or an environment for creative artists. There's a real tension here because they're meant for different kind of practices. And I myself spent a lot of time thinking about this. And if you're really interested in this discussion, you should check out my dissertation, Adventures in Quantum Land, which is available online, and you might find some interesting things there. Another person asked, two people asked if it would be possible to share the patches. And you asked, and I delivered. So if you go to the GitHub, not this one, let's see, to the ICCMR page of the GitHub page of the Qtum project, which is under the ICCMR-Quantum GitHub username. You will several repositories of several of the things that we saw yesterday, and one of them is let's see here, Intro to Quantum Computer Music. if you open this repository, you'll see that the patches, all the patches for part 1 and including the notebook that we created on Quantum Lab, as well as the Quantum Composer, everything is here, so you can download it. The installations are pretty straightforward. You need to have Macs, you need to have the QAC, you need to have an IBM ID account. Yeah, so that's covered. And last, someone's asked, did anyone else get a Qiskit backhand not found error when trying the hardware? Works fine from the composer, but not the lab. Okay, I'm not entirely sure what can cause this error, but my educated guess is that maybe you mistyped the backhand name. You can double check the if you navigate to services and then here, and these names here are the names that you need to type when you're requesting access to a hardware backend. Let's see if I can quickly jump to the lab notebook that we had yesterday. People mentioned this is small, so let me focus in here. Okay, which one is it? Maybe this one. Yeah, so here, when you ask provider get by hand, make sure that this name is correct. And probably there's a way for you to check what are the providers directly from the Quantum Lab Python notebook. So I just executed the first cell so that everything is imported. I think if we type provider backhands like that and execute this cell, yeah, it prints out the names of all, well, the simulator as well, and all the other devices that we have access to with our account. Sieglinde might give some more insight into how to apply for, researcher or be part of the researchers or educators program. Back to my presentation slides here. Yeah, someone else also asked, have you tried implementing qubits while in superposition without measurement? I wonder what that would sound like. Can we possibly utilize the imaginary part of the quantum state? This is such a great question. And because, one of the most intriguing things about quantum computing is actually to try to understand what goes on inside the quantum computer, how quantum mechanics works, and what is the actual quantum state. So there's been different attempts to try to represent a quantum state. I believe yesterday we saw some people using a couple of people using a sphere and then drawing like arrows to point from the center of the sphere to the surface of the sphere to represent a vector for the state of a qubit. And if it's pointing up, it's in the 0 state. Pointing down, it's in the 1 state. Anywhere else in the surface of the sphere is a combination of 1 and 0 and different phases, etc. And that is a really great way to visualize the states of a qubit, but it kind of falls apart when you're trying to deal and especially qubits that are in an entangled state, because otherwise you'll just have in the block sphere you can only have like independent qubits. So a while ago, people at IBM started thinking about an alternative way to represent this, and they came up with something that they called a Q-sphere, which I think is wonderful, and I spent some time studying it, and actually I actually recreated it in the QEC. So again, if you need to have the QEC package installed, if you have Macs and you navigate to the packages, you just go to the second page because it starts with a T, and then you install it there. And once you have that installed, let me open up a new patch. You can start a JS UI object, which is a JavaScript user interface graphics. And basically it's just like a slider that is more visual. And if you right click it and you go to prototype, you have different types of visuals. And I added one prototype that is called the OSC-Qsphere. That is basically the Qsphere. And if you right click this, and you can open the help patch for this, which is a faster way for me to explain this to you. So let's see, let's imagine that we have first just one qubit. And if we get the state vector, let's see, an expected state vector. If we add some gates to it, now it should be, we should have flipped the state of the first qubit. So now it's at the 1. And if we have, let's say, instead 2 qubits, I'm recreating the circuit and then creating the Bell state that we used yesterday. Now we have either 0, 0 or 1, 1. And you can create more complex circuits and try to visualize them. And it's kind of fun to just see, okay, if I have 3 qubits, this is how it would visualize them, distribute them, the states here. And actually, let's do first 3 qubits and add another MART gate to all the qubits. So we'll try to explore the space with all the 8 possible states, and it looks something like this. And you can rotate around and try to navigate and try to understand this, visualize this state vector space. And of course, if you try to mess around with different gates and add some rotation and change the phase, you're going to start to have color change to indicate the phase. And yeah, it's just a very cool way to try to visualize and understand. And there's no reason why you shouldn't try to sonify this. What we're doing here is, instead of asking get counts, we're asking get state vector. And so it will spit out the state vector that looks something like this at this point. So the real and imaginary parts. I hope this answers your question. This was not the original project is a project by IBM. I tried my best to pinpoint exactly the moment in time it was created. I was only able to have Jay share some drafts of the first drafts of this idea, but it was somewhere in the at the core of IBM that they came up with this idea. All right, back to my slides. Simon, excellent presentation. Thank you. Thank you. Beginning question: what separates your implementation through quantum computing and just doing random 8 instead of 3 qubits? All right. This first of all, thank you for. You might think this is a beginner question, but this is actually a very advanced question, or it actually requires. There's a lot to unpack here. So let me think for a second. First of all, using my example yesterday, that was basically recreating a random number generator, was using quantum circuits, and it was a very basic example of using QC with a didactical purpose in mind. Second of all, I would state that there is no simulation of a quantum system in a classical machine that will run faster than any other classical algorithm in a classical machine. but to prove that a quantum algorithm will run faster is like the challenge of a whole community of researchers. And then I would also say, actually pointing towards a more deeper problem and fascinating problem with quantum computing, which is related to the following problem. If you ask a quantum computer to perform a computation for you, how can you know whether it has really followed your instructions or even done anything quantum at all? And you know, this might seem like such a basic question, but it has profound implication. It's related to computational complexity, and it was actually the work of a then graduate student, Hurmila Mahadev at UC Berkeley. She spent 8 years thinking about this. She was working with Umesh Vazirani. And I was lucky enough to attend one of her lectures when I was at UCI, and it was amazing to see how you can pose a problem that sounds so simple and then actually a very complex problem. How do you know? How can you prove classically that a quantum computer is actually doing something quantum? Anyway, there's a lot. This is to say that this is a great question, and there's a lot to unpack here, but we need to move on. And I'm just going to start with a quick recap. So previously on IQCM, Intro to Quantum Computer Music, we started by creating a quantum circuit using the quantum composer. Then we decided it was kind of limited. We were running just one shot at a time. And then we looked at the menu and saw, oh, there's a code editor window. We saw some Qiskit code. We copied the whole thing. We brought into the quantum lab, and we were able to simulate it. And we were happy to see that our circuit was there, and we were able to actually simulate it and have some real counts. Then we decided to learn some math. Hardcore Python programmers and cube docs. We learned the Max side of Max. We learned the MSP side of Max, and we also learned the jitter side of Max. But we also learned how to reverse the flow of time and trick chickens into moonwalk they were back into the chicken coop. Anyway, after that, we were on a break. And after the break, we came out to Max. We came back to Max to explore the new, the QAC toolkit, a package for Max that I was basically developing the last 8 years that allows to build and simulate quantum circuits inside Max without even touching Python. We decided to then first recreate our original circuit at the beginning of the session in Max, and it looked like this. But now we are also able to simulate it, and we saw some counts. But wait, we are also able to get some Qiskit code, and we asked OSC-Qasm to automatically generate some Qiskit code. We copied the whole thing, came back to the quantum lab, pasted it, and less lines, and so neat. And then we decided to actually use a real hardware, but then we had to wait. And we didn't want to waste our time just waiting for the results to come back. And so we decided to create some sick beats using quantum circuits in Max. Okay, that's what happened yesterday. That was my quick recap. Just in case you're wondering, if you're just joining and you're wondering if you missed something. So one thing we didn't get to touch yesterday that I really want to present to you today is the UDP-Qasm project. And this is a project that I worked on with Paulo Itabraí, who's my co-pilot. And it is available on the ICCMR Quantum GitHub page. So if you go to the ICCMR Quantum GitHub page, you'll see the UDP-Qasm project, and there are some really neat instructions. And what is it basically? It's a simple UDP Python interface for executing Qasm code, or a simple bridge to connect the QAC toolkit with real quantum hardware. So when we build circuits in in Max using the QAC toolkit, and I'm just going to quickly build our circuit again. Let's imagine that I don't have the license for Max and I need to recreate everything from scratch. We can also, we saw that we were able to retrieve the Qiskit code, but we are also able to retrieve the Qasm code. So I'm just going to recreate again the our bell state. So measurement gates between qubit 0 and classical bit 0, and measurement gate between qubit 1 and classical bit 1. All right, that's the quantum circuit. Then we actually need the simulator. With that quantum circuit, doesn't matter the number of shots because we're only retrieving the Qasm codes. So we use the name of the simulator and ask get Qasm. If I use the word text box, it will just create a pop-up. So we can copy this and go to the, what is it called? The quantum composer, yes, here, which is fast to load. And here, if we have the code editor enabled, if we are seeing the code editor, again, you can toggle that here and it shows on the side. We can click here where it says Qiskit and we can swap between Qiskit and Qasm modes. So this is the Qasm code for an empty circuit. What happens here is that if I go back to Qiskit, you see that this here says read only. So you cannot change anything here, cannot edit in read only. But if you go to Open Qasm, we can actually start messing things around. Error found, obviously. So let's remove all that and paste our circuit from OCS.micro Qiskit, and we see that we retrieved exactly what we wanted. Great. So what is Qasm or Open Qasm? Open Qasm stands for Open Quantum Assembly Language. And so it's kind of a common language for the machines to interpret. So hopefully it will be the thing that will be common in all quantum computing frameworks, is that they all can either read from or write Qasm codes and send to the machines to interpret Qasm code. And you version 2.0, which is the one that is currently being used, is great, and it's widely adopted in the works, that has so many more features to control the real hardware at a pulse level, but it's not yet widely available. So what I thought was, how can I make this process of building a circuit in Max and sending that circuit into Python or a Qiskit environment to run on the real machines faster, without me just having to open a text box, copy everything, and do all these things manually. And that's why the reason why we created UDP-Qasm. And so I'm going to walk through basically setting this up. We will need some Python, but it's not too much, so don't worry. Actually, I will have to literally tutorial with you, because I don't even believe I have Python here. Oh, Python 2.0. I think, yeah, Python 3.6. So don't worry if you never used Python before. This is going to be, we're going to do this together. And for the differences between Mac and Windows, we'll have Paulo Itauraí jump in to say what is the Windows equivalent of doing this. Sounds good. Is everyone okay? Do we have questions so far? Some burning questions? All right. So first things first, we need to make sure that we have Python. And now I might actually need to use a real browser. So let's use this one. I'll just go to github.com/ISQCMR-quantum and do everything from here. UDP-Qasm, we need the Python 3.6 or more. I've been working with 3.7. You can use the version you want, but I know that one is really solid for, well, this is also a newer macOS. So we'll see if we'll run into trouble. Let's just go with the regular version. All right, save it. And I'm glad we have the majority of the listeners are Python experts. So if I do something wrong, please just let me know. So you'll have to accept this. All right. And when using the installer on Windows, make sure to add the option add Python X version 3.6 or whatever to path. In order to try our Max patches, make sure you also have Max, check, and QSC, check, available. Clone or download and unzip this repo. Sounds good. There's some things happening here, but it's still installing. All right. So we can also download this repo. Let me open that up. And it will look something like this, basically the same thing that we have there. Okay, so far so good. So I wonder now if we open the terminal, and we type Python terminal. On Windows, it's called the command line.
Prompt, actually.
Command prompt.
Sorry.
Thank you. So if we just write Python and press enter, it goes to 2.7 again. I wonder if we have to type Python 3. Okay, now we have Python 3. Great. All right. So what I will do is to follow the instructions. That's what I should do. So open the terminal and navigate to the folder where you saved the repo. Here's a refresh on how to use the terminal. Basically, we need to use CD to change directory. I'm going to change to the documents folder, and I'm going to make a directory called IQCM underscore part 2, of course. Now I'm going to go inside this directory, IQCM part 2, and then create a Python virtual install. Important because if you start installing things just directly in Python and you're working on multiple projects, you might end up with different packages for Python that will sometimes conflict with each other. So a good rule of thumb is when you start a new project, you start a new Python environment. So Python 3-m virtual environment, UDP-Qasm. That's just a name. You can name it whatever you want. Depending on your system, you may simply type Python-m. Yeah, so you can check if you just type Python and it gives you the Python 3, then you're good to go. You don't have to say Python 3. Enter your new Python virtual environment. On a Mac, you just type source. Now it's the name of the virtual environment, UDP-Qasm bin activate. And at the start of the terminal prompt, it should show UDP-Qasm indicating that you're in your new virtual environment. That is correct. Update pip and setup tools. I usually always have to do this because my system is old, but maybe because I just installed Python here, it would be not necessary, but it's a good measure to make sure that you have pip and setup tools up to date, because we're going to be installing an up-to-date version of Qiskit, and it usually likes when you have these two things up to date. And then install Qiskit and Python OSC. So we'll type pip install Qiskit space Python dash OSC. And now we wait. It usually takes, I don't know, 2-3 minutes to install Qiskit. Oof. Can't even change this. Okay. Okay, better now. All right. And also copy UDP_Qasm max folder into your max library. So when you download this repository, there's like this folder here that comes with a couple of files that are good for Macs. What this basically is an abstraction or a kind of customized object for Macs named UDP-Qasm, so that you can easily reuse. But there's an example patch here that we'll be using. But if you want to use later in your work, you can just go here, copy this, go to the documents, Macs 8 library, and paste this folder. All right. There. Let's see what happens here. Still installing. In the meantime, are there any questions?
We have some Q&A.
Yes.
I think Samuel is having some trouble with navigating the terminal.
Mm-hmm. There's here's some resources to double check how to navigate your directory in the terminal. I myself have to review them from time to time. The question was, oh, I'm seeing now, Python isn't playing ball. Apparently my CD documents message has invalid syntax. Ooh, make sure that you have space between CD and documents. Or in no space before CD, I guess. Yeah, maybe other users in the session might jump in to help. Okay, still installing. All right, Paulo, do you want to system just try to quickly navigate through these first few steps?
Yeah, we can do that on Windows. I can share my screen. Just a second. Okay. So let's just try to follow the same instructions that Omar did a while ago. So I'm just going to read the instructions. There was a discussion on the chat that is maybe going to this direction of Python installations. And my recommendation is really that on Windows and maybe on Mac, that you install some Conda distribution of Python. So I mean, for example, Anaconda, which is a tool, yeah, it's a whole distribution of Python in which you have a lot of libraries pre-installed, and you have a very safe and reliable environment for installing and running Python code. In a way, it's less prone to errors when you are installing packages, at least on my experience. But of course, you can also try to download from the original site, python.org/downloads. If you go to downloads, you have some Windows distributions here. And then you can download any version that you want, maybe Python 3.10, or, well, we can try to download that. I don't think I'll actually install Python again, since I ran with some conflicts between Anaconda and Python. But I can just show where the download is. Well, right here, you can go to the Windows installer 64-bit version. And if you are looking for Anaconda, you can have on the main website that just you can go to products, individual edition. It is a free edition you can use for your own purposes. And then you have this download button. So let's try to follow the next steps. After you have Python installed, you open a command prompt. Or if you have Anaconda installed, you can open an Anaconda prompt. Okay. And the recommendation is to run as administrator. You have to allow this. Then you are presented with this nice screen. And then you need to, you have also need to download the repository as well, of course. So let's just do that. You just click download. Okay. So we can unzip it somewhere. Of course, we all pay for WinRAR, right? Well, maybe I'm going to save on my desktop. Or I think I have a location for that. Here, ISQCMC, right. Okay, so if I go to my files, I can see the file there, so just to be sure. So it's on C, users, this beautiful username, ISQCMC, and here you go. We have the same packages. So we need to navigate to that. Since you are in an administrator session, you need to actually go back to the root and then go into your directory. So the way to do that is really to type cd, and then you say c, then you type users, and then maybe it's, backslash users backslash your username, and then you just continue navigating until you reach your destination, which is the file UDP-Qasm. Okay, so this shows, the prompt shows that we are on this file, on this folder, sorry. And we can look inside the folder using the dir command. And now we run the same things. First, we can check which Python version we have. I think on many Windows distributions, you just need to write Python. You don't need to write Python 3. We can check that with Python -- version. So I have Python 3.8 installed. So now we need to create a virtual environment as recommended. We can see that Anaconda already has a virtual environment. It's called base, but we are going to create a new environment and load this new environment just for UDP-Qasm. So we just write Python -m VM, and then you just write some beautiful name that we record. And then it takes a while. All right. Then you don't need to use the source command. It actually doesn't exist in Windows. You just write the script, the directory of the script, and it activates. So we just do UDP-Qasm, UDP-Qasm, then \. I'm just hitting tab until I find it's just looking for some similar entries. So now I find my UDP-Qasm, which is the same name of the virtual environment, and \ scripts \ activate, then enter, and now we can confirm that we are on the UDP-Qasm environment. Now let's just do some upgrades. So pip install upgrade pip setup tools. Enter. So now it's just updating things. I hope that it comes to an error, because I want to show a possible error that you can have. Okay, we had the error. So sometimes when you run some code and it just go to error, you just say, well, let's just run it again. Just check if it was just maybe something of the destiny. But when I try to run it again, oh, I have Avast. That's why it's running 2 times. Maybe I can disable Avast. Okay. So it did work this time. Okay. it just okay. But if you run into some problems, there is a problem with this command, the upgrade pip, that it uninstalls a pip itself before it installs a new version of pip. So sometimes you run into an error that you need to reinstall pip to keep going. And for that, we have this link right here. And then you just run these 2 commands, starting here, curl, this curl command, which installs pip again, which downloads pip, and then it installs pip again. Okay. Now let's just install Qiskit and Python OSC. Oh, I have already installed, but I can actually try to force. Or maybe we'll have enough waiting. If you run any troubles with installing Qiskit, let me know. I'll try to help. Do you have any questions? image to upgrade pip via Python, pip install, upgrade pip, instead of using pip directly. Okay, that's a good idea. Maybe you just prepend this pip install. Oops. Instead of just using pip install upgrade pip, you can actually try to just Python -m and then you run the same command. Good recommendation. So I think we are at the same point, right, Omar?
Yes,
you want to switch back?
correct. Yes, I mean, if you'd like to continue, just since you're already sharing and show the patch working.
Okay.
There, that would be great. You
So
already
we
have it open.
Okay. Oh, let me open the patch. So if you go to the folder where you downloaded the UDP-Qasm, you will see a patch which is called example, or actually you have UDP-Qasm Max. Oh, I haven't done this. Sorry. So you might want to put this on the library folder inside Max. So you just copy, and then you go to the folder where your local folder, or the configurations inside of a Max path where Max can see something. So that is usually on documents, Max 8, library. Then you can just go here. Okay. Another way of doing this is just by doing on Max. You can doing options, file preferences, and then you just add. For example, I have added a path with UDP-Qasm. So now we can just open the patch. We have a patch and a help file. Let me do the help file. Okay. So I don't think I have the final version of MicroKiskits. So I have this error, console output is not implemented on the version that I have, but that's not a problem. So this patch is really straightforward. It's very similar to what you've been doing so far. We just create a circuit with named QC with 2 qubits. And now we are going to build the same Bell state circuit that we are doing on this tutorial. So we do just a Hadamard gate, a CX gate, and 2 measurements. And now we are going to just get the Qasm code with this message, okay? And we can see on the Max console that we have generated the Qasm code. Now we are going to connect this with our Python interface, and this is going to be done with OSC Open Sound Control communication via UDP. So if you open this subpatch, this abstraction UDP-Qasm, you can actually see some arguments. Maybe OCH can explain this better. But the important object that I want you to look is the UDP send object, which is sending all of the data, all of the Qasm string into the internet, but where actually locally, just sharing on the local network through port 1416, okay? Now let's just try to run UDP-Qasm. So we have the terminal, we have installed everything, hopefully. And then we just run the code using this command. So Python UDP-Qasm.py. And you should have these 3 messages. First, the UDP-Qasm message, and then it shows where it's receiving and where it's sending messages on the network. Since this is a local network, we are on the same computer, we are going to use the local IP, which is this IP 127.0.0.1, which is the local host. This is the same. This is the same IP. When you say mean local host, you are meaning actually this IP. So we have now a Python interface that is working, and on the Python side of things, they are listening to the internet on this port 1416, and when they wish to talk, they are going to talk in this port 1417. It's just imagine that you have ears that are listening to a different room, and then you talk to an even other room, yes, and then you just have the opposite setup here on Max, when Max is going to talk to the internet using port 1416 so that UDP-Qasm can hear it. And when UDP-Qasm sends messages to the internet, hopefully Max will be able to hear it through port 1417 using the UDP receive object. Okay. So now let's just, since now the UDP-Qasm is running, oops, let's try to run this again and see what happens. We are going to just click get Qasm, and we can see that UDP-Qasm has received the message and it has done something with it, and then it has actually run a simulation, and then it sent back the result counts to Max, and we can actually see that on the Max console, the counts from 00 and 11, since this is a bell state. And we can actually run this several times by just clicking, and we can see that this is working. So maybe I can pass back to OCH, and he'll do the Macintosh part of things and also explain with more detail the Max patch. Does that sound good, Omar?
Wonderful. That sounds wonderful. Thank you so much. Everyone should give a big round of applause. That was a very, very nice presentation. It so happens that installation here on my side is still going, so I need to move on to my other machine as a backup plan on the fly. Let me bring Zoom into action here. Where is Zoom? Here.
Well, so if you are still trying to set up things, I can maybe explain some arguments and show the
you can
start
explaining some arguments, and I'll let you know when I am ready here.
Okay. So for stopping the UDP-Qasm.py program, you just go to the terminal and hit the classical Control-C, which is a command to interrupt everything that is going on in this terminal. It's really a hard push. You just plug out everything. And let's just look at possible arguments that you can pass to this interface. You can look at the possible arguments by just writing Python UDP-Qasm.py, and then you use a flag, which is all of these arguments that start with a minus. And then if you type -h or --help, it shows a help file. And then we have some arguments. So of course we can, if you want to change the default ports, the listening and sending ports, you can change that through setting up new arguments. You can also change the IP address if you want to make some communications that are outside your local machine. And then you have also optional arguments to log in into the IBM queue, into your IBM queue using your token, which is essentially this large string. I can actually show where your token is on IBM queue. Let me log in into IBM queue, IBM queue, IBM queue. Oh, that's lucky. I'm already logged in. So let me show. That's not the main page, is it? If you click on the top right corner on your the little person here, you can go to account settings, and in the account overview tab, you can see the API token, and this is just a really large number, a large string, and then you can just copy your API token. And this API token, you can actually pass as an argument here. So you can log in into your IBM Q account and use some hardware. That's the whole point of UDP-Qasm, right? Other informations that you need to pass to the UDP-Qasm in order to run quantum hardware is that you need to select a hub, a group, and a project. So let's go back to IBM Q. And the same account overview, you can actually go to the providers tab. And here you can see some of the providers and that you can access. So for example, as Qtune, the Qtune project has access to some systems. So we have this provider, and these three names here are respectively the hub, the group, and the project. So for example, I can just use the hub IBM Q and then use the group open and project main, which is the default, I think. Anything else? How is it going, Omar? Is everything
good? I can take it from here if you'd like.
Okay.
Thank you so much. Let me turn on my camera here. Where is Zoom? It always goes to another window.
Yeah, okay. I'm going to stop sharing here.
Yeah.
Okay.
All right. So thank you so much. Just for the sake of completion, I'm also going to show how to do this in the Mac side. So I have my virtual environment here. What is it? Yeah. I've followed the instructions on the website here as well. And I have everything installed. So once we are on the correct path, and I created the UDP-Qasm main folder with the contents of the repository. So here, right? It has the virtual environment with that name. We are logged in. We can confirm that through that message there. And so if we type Python UDP-Qasm.py-h, we can confirm that it will print the help file of that. As Paulo was mentioning, we can start UDP-Qasm.py, and it will say it's ready to receive some messages. I created a simple circuit here. Let me just show you here the console at the same time. So I'm recreating the circuit from scratch. I'm adding all the gates, and I'm gonna ask to retrieve the Qasm code, which it's gonna output on the OSC-micro-Qiskit object, correct? Now, instead of using the example patch that comes with the repository, this example patch, I have already copied this UDP-Qasm max patch into my documents, max 8 library folder. Well, where is it? Oh, max 8 library folder. It's here. right? So it's in the max path. So I now can instantiate an abstraction of that whole patch, that whole thing, just by typing on a new box, object box, UDP_Qasm. Sorry, UDP_Qasm. Double check for typos. If we double click this, we see that there's the core elements of those of the mechanisms of UDP-Qasm. So it's expecting to receive some Qasm codes. It will route a message starting with Qasm. It will prepend the qtune tag for the OSC message, add some other parameters that we can change. And then it will return whatever we receive. So if I send this Qasm message to UDP-Qasm, it should print something on the console and return something else. Here we go. We retrieve some counts. And if we click again and again and again and again, we retrieve different counts. And as Paulo was starting to mention, we can also use, as was mentioned here on the help file, our token to access actual quantum hardware. So let's see what it would look like if I had my token here. So I'll copy the token. I'll need to type. So I'm going to stop this. So Control C, and then I'm just going to print the help file again, Python UDP-Qasm.py -h, just to have that here, easy to access. And now I'll do Python UDP-Qasm.py, and to add the token, I type --token, I paste the token, and then let's see what happens if I just start this like this. Okay, it says UDP-Qasm, and it's receiving. So that in itself it says, okay, we have the token, but you didn't ask a specific machine. So in order to do that, we can do that through the Max environment now, if I am correct. Let's see the instructions here. Well, actually, we can see the instructions of UDP-Qasm if we right-click it, show the help patch. That's the help patch. But more helpful than that is the reference page. That's what I wanted. Okay, so it has different arguments. We can replace the receive port, the send port, the IP, the number of shots, and the backhand. Look at that. But these are positional arguments, so it requires these arguments to come in a certain position. If we just want to change just the backhand, then we can use an attribute. And this is true across several Max objects. So what are the systems that I can have access to? Let's see all systems, the ones that I have access to, one that is online, preferably Manila, IBM Q Manila. Come on, let me copy it. Okay. So back to Max, we can now set UDP-Qasm with an attribute called backhand, and IP address, I need to correct that. And yeah, I need to correct that. And the name of the backend. So if everything is correct, I'm gonna reset the circuit. It's recreated from scratch, recreate the gates, and then ask the Qasm code. So it's sent here, and it's running on IBM Q Manila, and it now prints to the console saying job status, job is queued, and it's in position 20. So there's 19 people ahead of me. Maybe you guys were faster than me and just started submitting code. So shame on you for not allowing me to demonstrate this in real time. I know we've been talking for an hour straight. I wanted to have a little break, but if there's any burning questions right now, that would be a good time to also address them. replace pin. All right, now it should be good. Welcome back, everyone. Let me know if you had if there's new questions in the meantime. That would be a great time to ask them regarding this or the thing that we've touched base on during this tutorial. I was just quickly checking the program. This session only runs until 10:30 because then we have the research paper session 3. So I could now just talk a little bit, explain some things, a couple more things about the UDP-Qasm project, and then leave some time for some last minute questions. I'm going to close this for now and open again. I think I installed UDP-Qasm on this machine as well. UDP-Qasm. Great. So the way,
Omar,
yes,
just I think I'm going to switch systems for the paper session, so I'm gonna need to leave you with the rest of the tutorial. Okay.
that's good. All right, sounds good.
So thank you, everyone. Enjoy more of Omar.
So when we open this UDP-Qasm object, we can see that there's a pencil here. So right now it's really locked. We're just in read mode only, but we can actually click this pencil and crash max. Let's try that again. And you can see that sometimes things don't go according to plan, and it didn't. I need to double check why it didn't install here on this machine. There might be several different reasons. Let's see, let's try to reopen. And let's try to actually open the patch directly. So it is inside the libraries folder, UDP-Qasm, UDP-Qasm max patch. So the way it works is that we have this patcher args object that takes care of any arguments that we might type into the object box. So if we say UDP-Qasm 1111, then it will use that 111 as an argument, and it has some default values for the arguments. The first one will be 1417, 1416, localhost 1024, and Qasm simulator. What this means is that the positional arguments for this object are optional. You don't have to type them in order for the object to work, but you can type them and in the correct order. But if you don't type them, there's already default values for each of these positional arguments, including the backhand, which is Qasm simulator. So that's why it, by default, if you don't type anything, it runs really fast because it's just using a simulator and not a real machine. It also has the attributes that you can set using the little @ symbol and then the name of the attributes. So if I just want to change the receive port, I just add the first positional argument, but then I don't want to change anything else, and I just want to change the number of shots. So I can use add and start typing shots, and then the number of shots that I want to configure my Python Qiskit environment. So now we will be using 100 shots. And then what happens is that we bring together all these messages. We use some of these parameters and arguments and attributes to change the UDP send and UDP receive objects. And we bring together what we need to send to the Python environments on this port. And then we also print what we receive. If there is an error message, we also print in red on the Max console, and this is how we do that. So this is a little bit of an insight into the software engineering part of a Max object, if you will. All right, so we're getting in the last 13 minutes of our tutorial. There is so much more that we could talk about, and I can't wait to hear the presentations and hear more and experiment with the proposals of other people's. Try to recreate them. That's my challenge for you. It's to look at what other people are proposing and try to recreate those circuits, like the chords from Satofumi-san yesterday, or the Basak-Miranda algorithm. How cool was that if you could just write that inside Mac? You can, and it's actually something that we've done already here on at ICCMR for the Qtum project. So I wanted to open my slides that have gone away since Max crashed, and here they are. So we've gone through the questions, through that, and then I promised I wanted to try this again to set up a new mind map. At the beginning of our session yesterday, we used this, and it was really fun to see your answers. So if you'd like to join for 1 second and last mind map, that would to have an idea of what does it brings in your mind when you hear quantum computer music. If you have a phone, you can scan this code, or you can just go to menti.com and use the code 36966381. And I can also share on the chat direct link. Let's see, copy, chat to everyone. And we are starting to see some results. Let me refresh this. All right, randomness is a big one now. Great. Install. Sorry. University of Plymouth, now it's in the map. Sonic possibilities, very good. Probabilities, great, perfect. New music and experiments and superposition as well. Let me refresh. I actually, unfortunately, need to do the refresh manually here. New instruments and future and innovation and performance. Noise, yeah, that's a big one. Expression and experiment. That's an interesting one. That now it's more clear that this is maybe an avenue of to enable more expression. So I'm gonna try to save these mind maps and actually upload both on that GitHub repository so that we can see the before and after. That would be a fun thing to do. All right, we're on the last 9 minutes. I would just like to just recap the idea of quantum computing, just to make sure that it is clear for us. Let me double check if I have the board ready. Here. All right. So we learned that quantum computing is a probabilistic means of computation that makes use of quantum mechanics phenomena like superposition and entanglement. And we learned that if we have a problem and we want to use a quantum computer to compute our solution, we still need a classical computer. And we need a classical computer to write quantum circuits using quantum gates. And then we pass this information or set of instructions qubits on a quantum computer. In effect, this is these instructions are converted into a series of pulses. And I saw someone on the Q&A or chat yesterday was explaining that. Thank you for doing that. And then computation happens and quantum mechanics takes place. And then finally, in order to retrieve the results, we have to perform measurements. But our measurements are only limited to zeros and ones. So they're classical bits. We store the information in classical bits and we read the information, the solution using a classical computer. So this is one very important thing to have in mind, is that we use classical information, we send classical information, and then we make use of quantum information to compute our problem. But then in the end, what we retrieve is still classical information. Just wanted to have this recap just so that it's clear that quantum computers are not going to just replace everything. We'll always need to use them in conjunction with our current classical machines. So we are 5 minutes early. This is has been a pleasure. Again, my name is Omar Castanamido. I can't wait to see the rest of the presentations for this symposium. And I'm looking forward to seeing you and interacting with you as much as I can.